Hello. So let's talk about the modern periodic table. And let's talk about how it's arranged, why it's arranged the way it is, and some of the patterns, the repeating patterns, the periodic patterns that are present in the table. So, one of the first things I want to do is go through, weirdly enough, electron configurations, right? We know that the modern periodic table is arranged by atomic number. So we know that in the modern periodic table, that's one proton, two protons, three protons, four protons, 5, 6, 7, 8, 9, 10, 11, 12, and 13, 14, 15, 16, 17, 18, 19, 20, 21, and so forth. So we know that protons increase in the periodic table as we go across. And if we know the number of protons, we also know, assuming it's a neutral atom, the number of electrons. And so what I'm going to do is I'm going to draw in the electron configurations for each element in its respective box. I'm not going to do the whole electron configuration. I'm just going to do the last part, the last entry of the electron configuration. You know what? Let me just take you through it and show you what this looks like. I'm going to take you through this one. This is hydrogen and only has a 1s1. This is helium and it has has a 1s2. And then we know once the first energy level and sublevel is filled, the next sublevel is the 2s. And that would be a 2s1. Why is it just a 2s1? Well, because remember, for lithium, this would be lithium here. Lithium would be 3 electrons. That'd be a 1s2 and a 2s1. So I'm just going to show the last part in the box of the configuration. And if I keep that kind of situation going, the next one for beryllium would be end in a 2s2. And then after the S ends, we know that the P's would start. So the last part of the configuration here would be a 2p1, and then a 2p2, 2p3, a 2p4, a 2p5, and a 2p6. And then when I get done the 2p's, well, again, if we follow the order of configurations, I end up with 3s starting. And then when the 3s's end, I start filling in the 3p's. And you could, do any of these configurations, and confirm what I'm writing down. But you should be seeing something. When the 3p's end, then we go to the 4s's. And when the 4s's end, that's when that overlap starts to begin, and then we enter the 3d's. You can see, hopefully now very clearly, that the periodic table is really just mapping out the electrons and electron configurations. Because when the 3Ds end, according to what we've done, then the 4Ps start. And that should make sense because look at everything above it. Look at all the Ps. Look at how they're arranged. And then when the 4Ps end, of course, the 5S's start. And then, of course, you got the 4Ds. 4D1 all the way to 4D10. And then when the 4Ds end, the 5Ps start. 5P1 to 5P6. I'm not going to write them all in. And then the 6S's start. And then what happens is the 5D starts, but then something peculiar happens. If you watch the periodic table, there's kind of a break here because we kind of jump atomic number right here. And between this box and this box, we end up actually first taking a side trip down here. And so if you look at the atomic numbers, and you can see that, you can see that here, we're going to go from 5D. Now, I ignored this before, but really the 5D kind of does start before the 4Fs. So really what we were doing before, and it was a little bit of a lie, I told you it was a little bit of a lie, but we, in a previous work, we did 6S1, 6S2, and then we went to the 4Fs. And you can see it's going to go all the way across. Well, guess where this is going to end? 4F. How many can an F hold? 14. And then when that ends, when this whole row ends, you're going to jump back to here. So what this is doing is showing you something about the periodic table which you might not have known before. Really, this periodic table should be split right here. This periodic table that you see is kind of an abbreviated version, not abbreviated, but it's an adjusted version, because really the periodic table should look like this. Right here, this section here, this section was cut out and brought below the periodic table, below the main level. And then these two sections of the periodic table were squished together to make the version that we know generally. That's because these are what we call rare earth metals, and they kind of do their own thing. And we don't use them that often because they are so rare. So we brought them down below. And then, like I said, squished these two sections of the periodic table together to make what you see here. So that would be, let me actually make this a little clearer. You know, we would cut that periodic table kind of right here and squish it together. But what I'm really trying to show here, and of course, actually before I do say that, what I can do is I can continue this. I can do a 6B1 all the way to 6B6. Then we go 7S1, 7S2, and then here we would start the 6D1, and then we would jump down down here, and when we do the 5Fs, we go all the way across to 5F14, and then we would jump back up and continue with our 6Ds, 6D10, and 7P1, and you go across. And if you follow that, awesome. What I'm trying to show you is that the periodic table is really just an arrangement of all the electrons in a configuration in such a way that, notice, the same electron configuration happens in every column of the periodic table, right? These are all ending in S1s. These are all ending in P4s. These are all ending in, like, you know, these would be all D5s. I didn't write out the D5s, but they would all end in D5s. And what that means is, because they all end in the same electron configuration, that means those elements in that column, in that up and down column, are going to have similar behaviors, because it's electrons that dictate the behavior of elements. So, you know, if all of these have the same ending electrons, all those elements are going to behave very similarly. And that's what Mendeleev did. Mendeleev put elements in columns that behave similarly. He didn't know about the electron structure then, but all he knew was that they behaved in similar fashion. And so your periodic table shows you that, you know, the pattern of repeating behaviors is evident. That is especially clear if we isolate, what we call the representative elements, which, if we take this section and this section, right, we can see that, I went over this with Mendeleev. We have the red, the orange, the orange elements, the yellow, the green, the blue, the brown, and the black. And then what Mendeleev didn't know about at that point was what we call the noble gases, these pink ones, because they're non-reactive, so they did not have enough opportunity to see how they would act, because they didn't react with anything. So all of this is important because, one, again, elements in the same column have similar behaviors. Secondly, it's also important, and I'm going to erase all of this, or a lot of it, because it's really messy. Well, I'll erase it in a second, but what I want to show is it's also important because note that each row, as I stated before, really shows you that the energy level being started, right? These all belong in the first energy level. These start, and for the most part, are all second energy level. These are all third energy level, if I'm reading it across sideways, right? This starts the fourth energy level. Yeah, there's some third energy levels because of the way the D fills, but it starts the fourth energy level. This starts the fifth energy level. It starts the sixth energy level. It starts the seventh energy level. So now what we need to understand is, since this sixth energy level has this split here and comes back down here, remember, this was part of the sixth energy level. Remember, I can show that here because, 1, 2, 3, 4, 5, 6. So that went all the way across. So that took into account that part that we had cut out and put down the bottom. And same thing here. If this is seventh energy level, this split here continues here. So this is all seventh energy level, this whole thing. So really messy, but here's the main payoff. This is the main payoff. And I'm going to clear all this out of here. All of it. All of it. Bye-bye, bye-bye, bye. Get rid of all this stuff.